With our classification scheme finished, we now have an overarching picture of what thermodynamics is really about. We take some formula for a free energy that we essentially make up or concoct in a way that we maybe have an educated guess that it might work well. So we begin with a formula for a thermodynamic potential in terms of its natural variables. Our next step, once we have this thermodynamic potential, is to take derivatives of it. So we take derivatives with respect to the natural variables. Those derivatives result in explicit expressions for what we've called the conjugate variables. These expressions are also known as equations of state. The ideal gas law and the Sackur-Tetrode equation are actually equations of state. Once we have these equations of state, we can then take derivatives of the conjugate variables with respect to the natural variables to get response functions or Maxwell relations. The response functions are what are most closely related to experimental tests. If the predictions for the response functions of a given model match the experimental data, then we conclude that that model may be a good representation of that system. Alternatively, we may just take a phenomenological approach. Say that the thermodynamic potential has some general form, perhaps a polynomial or a certain function with logarithms that is known to work well, and then turn the crank to get the equations of state, turn the crank again to get the response functions, and do experimental fits of those response functions to determine the coefficients that were in the thermodynamic potential to begin with. The way that a thermodynamic potential is guessed is in the realm of statistical mechanics, and we'll come back to this later on in the course. But this gives structure to all of the equations we've had flying around from day one. Internal energy was a potential. We began with the ideal gas, equations of state. And we know from equations of state, these are essentially equations that determine the derivatives of the potential. And just one equation of state, say the ideal gas law, can't determine exactly what function was used to get it from taking a derivative. So when we start from equations of state, we're starting in the middle of a process and we don't quite know where things are going. When we start with a thermodynamic potential expressed in terms of its natural variables, we have an explicit way to derive all of the thermodynamic information about that system. Therefore, a thermodynamic potential, in terms of its natural variables, constitutes a complete theoretical description of some system. We call that a thermodynamic model. Let's see how this works out in an example case. I'm going to make up a model. This model will be expressed in terms of a Helmholtz free energy. It will be equal to minus a constant parameter, A, times the volume of the system times the temperature to the fourth power. Then a second term is added on. Another parameter, B, which must be determined by experiment, multiplied by the number of particles squared over the volume. The natural variables are N, T, and V, and that's what shows up here. And there are two parameters in this model, A and B. Those have to be determined from experiments if the model even works. So let's turn the crank on this and see what the predictions are for this proposed thermodynamic model. This seems very abstract. Let's take our first step and calculate the state equations. For entropy, I need to take the derivative with respect to temperature and make that negative. So I'll have AVT cubed times 4. So I'll have a minus AVT cubed times 4. The second term has no temperature dependence in it. Remember, B is a constant. So our entropy in this model is plus 4AVT cubed. Notice that the entropy comes out extensive and seems to have a reasonable dependence on temperature. More temperature, it's hotter, has more entropy. Let's work out the equation of state for the pressure. This is minus dF dV. We've got a minus sign up front from the definition. And then we have the derivative of volume to take in the middle. So we'll have minus AT to the fourth minus BN squared over V squared. This minus sign is the same one from here. This minus sign is from the power rule, V to the negative 1 power. Simplifying this slightly, we find that the pressure in this model is equal to A times T to the fourth plus B times N squared over V squared. Again, note that the scaling of this works out perfectly with an intensive pressure on the left. Temperature to the fourth is intensive, so it doesn't matter how many powers it gets. And then number squared over volume squared is an intensive ratio. Again, this pressure seems to make sense, even though it's clearly not an ideal gas. The pressure scales as 1 part with temperature to the fourth power, so it's hotter, it has more pressure, and also scales with density, so as its density increases, it has more pressure as well. So now it's clear that A, the constant A, will end up having something to do with heat and temperature, and the constant B will have something to do with compressibility and density. Let's continue for sake of completeness and calculate the chemical potential of this model. It will be dF dN. So N only appears over here, so I'm going to get a simple derivative 2Bn over V. Again, the intensive scaling is correct, and the chemical potential is essentially proportional to the density, N over V. So now that we've figured those out, let's put them in our pocket. We'll record them up here. So this gives us some feeling about how the model behaves, but our real test is going to be to predict the response functions of this model and see if they match any experimentally accessible systems. So since we're doing Helmholtz free energy, let's start off with the heat capacity at constant volume. This was equal to T times ds dt at constant volume. That's the definition of the heat capacity at constant volume. So ds dt is going to be 12 a v t squared. So simplifying this, I'm going to get 12 a v t cubed. So a t squared inside and a t in front. All right, so the heat capacity in this model depends on the volume, so it is extensive, depends on the constant A, and varies as temperature cubed. So this model describes a type of matter where as it gets hotter, its heat capacity grows without an upper bound. The second one that we will look at is the compressibility. Remember, the definition of compressibility was negative 1 over v dv dp at constant temperature and particle number. So how can we do this derivative? Well, if I take a naive approach, I might think, let's solve this equation of state for volume. Subtract AT4 from both sides, invert both sides, divide by bn squared, and then I'll take the square root, and that will give me an expression for volume. And that would work. But I don't want to do that on the board here because square roots are annoying and hard to write and messy. Let's see if we can come up with a more clever way of doing this using some of our identities for exact differentials. Notice that this derivative would be much easier to do if the function on top was the pressure, since we have an explicit formula for the pressure and we don't need to solve another step. We can exploit that by using the inverse rule. We're allowed to take the derivative of pressure with respect to volume first and then invert the answer. When we do that, this derivative will be negative 2 bn squared over v cubed to the minus 1 power per the formula. So our value for the compressibility will simplify to v squared over 2 bn squared. So our model describes a system where the compressibility increases as the volume grows and decreases as the number of particles grows. It's inversely proportional to the density. Well, that sort of makes sense, right? If a system has high density, it shouldn't be very compressible, has a low compressibility. If the system has a very high density, if volume is big, then it's easy to compress. So this system seems to behave somewhat like a gas in terms of its compressibility, but maybe not an ideal gas. The last thing that we should be able to calculate for this is the coefficient of thermal expansion. Remember that the definition for thermal expansion coefficient was dV dt at constant pressure and particle number. Now again, I'm faced with this problem of not having an expression for V directly. No, this is P and N. And there are several ways I could approach this. One, I could simply solve this equation for V, do the derivative that involves the square root. I might also be able to use the inverse rule on this by solving this equation for T. I would have to take a fourth root, though. That seems also quite nasty. Perhaps there is a Maxwell relationship I could use. The Maxwell, even though we're dealing with Helmholtz free energy here, a Maxwell relationship here would come from the Gibbs free energy. Let me consider that just by writing out in red. The Maxwell relationship that might be usable would be dV dt at constant pressure and particle number would be equal to ds dp at constant temperature and particle number. And I believe that for the Gibbs free energy, we've got a sign change on both terms because they're both intensive. And normally volume is coming in with a negative sign, so there will be a minus sign between these two. So is that going to work for us? Well, we've got a formula for entropy, but the entropy doesn't depend on the pressure, at least it doesn't right now. So if we wanted to use this Maxwell relationship, gosh, we would have to, solve this one for volume first in terms of pressure, and then use that to eliminate volume in the formula for entropy. So that one doesn't really seem to work out easy either. So it's not wrong. It would work, but it's not easy. Okay, so let's explore one other path. I think this one is going to be the one that works. Let's explore a identity of exact differentials. Do you remember the triple rule? Right? The triple rule would be in blue, dv dt at constant pressure times dt dp at constant volume times dp dv at constant temperature equals -1. The derivative we want is right here. It's the first one. dp dt at constant v. That seems easy to do, right? We have a formula for P in terms of temperature. So we could have this be, use the inverse rule on that. That would be easy. And dp dv at constant temperature, that's also an explicit formula. So that's very easy. So we'll modify this inverse rule here. We'll say I've got my 1 over v out front. Then I'm going to have my negative sign from the identity. I'm going to divide both sides by the dp dv at constant temperature. And I will move the dt dp to the other side and also use the inverse rule. So it will be dp over dt at constant volume. Okay, so that one looks like it's going to be pretty easy to work out. So I'll have -1 over v times a fraction. The numerator is dp dt, so that would be 4at cubed. And the denominator is dp dv. And dp dv is, we actually already did that one here, right? dp dv. So it's -2bn squared over v cubed. All right, and that is our formula for the coefficient of thermal expansion in this model. I think I probably could simplify this a little bit more. Let's see, the minus signs ought to cancel there. So minus cancels to a plus. I've got a 4 and a 2 that can cancel. So in the numerator I'll have 2at cubed v squared. And the denominator I'll have 2, the 2 will be canceled. So I'll have a bn squared. Okay, so that's our formula for the coefficient of thermal expansion. And, it doesn't look so simple. It's not obviously that alpha is directly related to one of these parameters, A or B. The thermal expansion coefficient depends on the current value of temperature, volume, and particle number for the system. But that's what this model predicts. And so it remains to compare with experiment to see if it's a good model or not. But that is sort of how turning the crank of these thermodynamic models works. We begin with a model. We work out its predictions here in terms of equations of state. And then one step farther in derivative land, we work out its predictions for response functions such as heat capacities, compressibilities, coefficients of thermal expansion, and others.